All right. Okay. Well, it's going to be a very few of you with who, right? Okay. But let's see here. Extra effort, I guess. Woohoo! All right. Woohoo! All right. Thank you. Okay. So this is experts again. Only the circles mean anything. I don't know what that means. Okay. So we're going to do lecture in a minute. So we talked about multiplicative weights, right? So what we're going to do is we're going to do prove strong duality for zero-sum games using multiplicative weights. Okay? So what is multiplicative weights? It says, in some sense, you have experts, right? You have the experts, and they're doing something. They're predicting what's going to happen today, or they have some idea, and then every day, that expert gets penalized or not. Okay, that's the idea of multiplicative weights. Okay, and so who does it get penalized by? It's this world, this adversarial world out there. Maybe it's adversarial, maybe it's nice. Who knows? We don't care. It could be like really trying to make the algorithm look bad. And remember, the algorithm itself, the experts don't care, the adversary doesn't care. Who cares is the algorithm. The algorithm is trying to pick the best expert every day. But it doesn't. It picks a distribution over experts. And then on average, it does about as well as the best expert. Okay? So that's the idea. So you have n experts. Every day, they do well or badly. And then over time, you're picking a distribution over the experts. You're picking an expert each day, and that gives you an expected value each day. And that expected value, you want to say that expected value over time is at least as good as, or at least close to what the best expert is. Okay, does that make sense? Okay, so in that frame, we're going to say that in zero-sum games, you also play distributions, right? Okay, so you guys, everybody saw the video lecture? or read the notes or something? So in two-person games, okay, let's quickly, rock, paper, scissors. What should I play? No, I should play a distribution. Okay, so that's what I'm saying. The whole setup of zero-sum games is not that you play a strategy. It's that you play a distribution over strategies. What is the distribution I should play over strategies for rock, paper, scissors? Yeah, 1/3, 1/3, 1/3. A distribution is a vector over the possible strategies. Okay? And you would play, what would you play? A distribution, 1/3, 1/3, 1/3. But if I knew, if you know I'm playing 1/3, 1/3, 1/3, what can you play? What? Anything. Your expected value, your probability of winning is the same no matter what you play. But should you play anything? And tell me what you're going to do? If I play rock, paper, scissors, and he says he's going to play paper every time, what will I do? Play scissors, right? So there's this sort of unfortunate thing that happens if you're not in equilibrium. But if on the other hand, if he tells me he's playing rock, paper, scissors, 1/3, 1/3, 1/3, and I'm playing rock, paper, scissors, 1/3, 1/3, 1/3. Both of us will just keep doing that. That's what's called an equilibrium. Okay? So we'll see that that's what the other person is doing. I'm not going to change. You're not going to change. We're all sort of either equally unhappy or we know where we are. Is that right? Does that make sense? Okay. Or equally happy. So this notion of playing a distribution is inherent in this zero-sum game viewpoint. And there's an inherent distribution in multiplicative weights, right? Each time you're playing a distribution over the experts and trying to find a distribution where you lose as little as the best expert, right? Does that make sense? So what we're going to do in this two-person games, there's these payoff matrices, and the payoff matrix for rock, paper, scissors, you can imagine what it might be. It's a 3x3 matrix in each entry. If I win, I get $1. If you win, you get $1. And if we tie, nobody gets any dollars, right? So it's just a diagonal of zeros and minus ones and plus ones in the appropriate place, right? And so now the column player, the column player plays a distribution. It plays a distribution over the column. the row player plays distributions over the row. I'm going to do this again a bit. But now you can understand maybe the rest of the sentences on here. I just did two-person games quickly. So column player plays this multiplicative weight distribution every day. You think of that as playing the columns. And now the row player will just play, if I tell you I'm playing 1/3, 1/3, 1/3, the row player will just pick one on rock, paper, scissors. The row player could just play rock. Okay? And if I decide to play paper, the row player will just play scissors. Right? Okay, so on. So this is, the row player will just choose the best response. But it won't be much of it's a distribution, but it's a pure distribution, just one response. So this is what will happen. And then we do this for a while. We just let the multiplicative weight algorithm work. And after a while, what we do is for the column player, we output the average of what he did over all time. And the row player will also output the average over what they did over all time. So if in the first step I play rock, in the second step I play paper, and the third step I play scissors, the average of that is 1/3, 1/3, 1/3. Okay, so that's so we're setting up a way to develop row and column player strategies using the multiplicative weights framework. Okay, so I'll do that a little bit, and this will be more. And then we're going to do, this is extra, it's not going to be tested, but it says that if you barely learn the material, you can learn it really well. Okay. Which is why we have about 51%. That's what the averages are on our tests, so that means you barely know. It's got nothing to do with our exams. But it says that if you have a bunch of points, and I can predict, and they're labeled plus minus, and I could predict correctly on a little bit more than half, 51%, then if I have an algorithm that can always do that, no matter what points you give me. So you give me a set of points with some feature vector that's associated with them, and I have an algorithm that can predict correctly or can predict all the labels correctly with 51% probability, that I can use that kind of algorithm many times and get an algorithm that predicts correctly 99% of the time. Okay, that's the idea. Okay, does that make sense? Okay, so that's what it says. So it goes from a crappy algorithm that only does well, like barely is better than just guessing, 51% of the time, to one that's barely worse than, being perfect. Okay? And again, it's this multiplicative weight application. What we're going to do is we're going to set up the experts here will be the points. The points will lose if an algorithm classifies them correctly. Okay? And the points are trying to not lose. Okay? But every day, the adversary will make sure that at least 51% of the points get categorized correctly. And so then, sort of on average, every point should be categorized correctly 51% of the time. And that means that, on average, the majority of days, every point is, for a particular point, the average for that point, the majority of days, it should have been classified correctly more than half the time. So if you use a majority algorithm, you use a majority. Your prediction is to take all the days and all these algorithms. Every day you develop an algorithm on a different distribution of points, and then you take the majority vote of that algorithm, and that will predict it correctly with 99%. Okay? Okay, so here's this matrix. There's a matrix, A, it's m by n, x times t. That's a vector. It's a column vector, right? xt times a, column vector. Shorthand, I may forget the t is what I'm saying here. So a times y is an m-dimensional column vector as well, right? Okay? Yeah, just remember what a matrix is. It's also on these boards back here somewhere. Yeah, there's a lot of matrices back here. I see them. Some singular value decompositions as well. So that's the row mix strategy. Now, mix strategy, again, for these two place order games, we're playing each row with the probability independently. And the column player also plays each column with a certain probability. The payoff is this xt times a times y, And this is because you could think of this as saying this is this A times Y. And now you're summing over the rows of xi times y. So this is a dot product of xt times a times y. You could have done it the other way. You could have done xt times a. But the key here is the aij. Okay, the aij says if the row plays row I and the column plays column j, the payoff is aij. And you think of it as if it's a positive number, the row gets paid. If it's a negative number, the column gets paid. So you think of it as this is the amount the column pays the row. So if it's a negative value, it's really the row paying the column. Okay? Okay, so this is a vector. Once you fix the strategy for x, you get a column vector, right? Now each one of these column vectors is basically the payoff vector for which the column gets to play. This is the row strategy. So after I tell you my strategy on rock, paper, scissors, 1/3, 1/3, 1/3, you can evaluate what your expected value is on rock, on paper, and scissors. And that's a vector. And that's this vector. Okay? And vice versa. If you tell me how you're playing rock, paper, scissors, I can just multiply the payoff matrix times y, I get a vector, and that vector tells me what's my expected payoff for each possible strategy for me. And my strategies are the rows, right? That's the rows that I'm multiplying by. So the pure strategy, when I say pure strategy, it just means one. I'm just picking one row. Okay, so that's a vector that they sum up to one. It's still a distribution, but the distribution is really focused on one strategy. Okay, the row maximizes and the column minimizes, and an equilibrium pair is one where I have a pair of vertices, a pair strategy x star y star. And the value is this. This is its expected value, right? Well, all I'm doing is multiplying out this thing, saying, what's the probability of me playing row times the probability of you playing scissors times me playing rock and you playing scissors, which means I get 1 times 1 because I win rock beats scissors, right? And then I sum up all these possibilities and the probabilities of all these possibilities. Again, that's what this expression is doing. It's xi times yj times a sub ij summed over all the entries. Okay, that's what that expression gives you. So that's just the value, the expected value that I was talking about before if both of the players are picking from this distribution independently. So now, what this is saying, look, if I fix x star and I let y do whatever they want, they can't do any better. Okay? So that's what equilibrium means. And similarly, if I fix y star and I let x do whatever they want, they can't do any better than how they're already doing using x star. Okay? Okay. So it says the max row, so this guy is some value, and we're saying it's equal to the max row. You're only playing, so this guy only has non-zeros on values where these are not maximum. Right? And similarly, this is the column can't do, the value of this game is equal to the value of the min column. Okay? Minimum expected value over columns after you go ahead and use this strategy on the rows. Okay? So again, the y star won't have any non-zero values for anything where this minimum is not achieved. Okay, so here's an example. Okay, this is rock, paper, scissors, and cheat. I talked about it in the lecture. The last row has an extra strategy. You see, so 0 means he ties, 0 means he ties, 1 means he wins. So you see the other rows, he can win or lose. But this last strategy is very nice for this cheater. It's the cheating strategy. It's rock, paper, scissors, and cheat. Okay, so I'm going to cheat. Okay, so and when I cheat, like if you play rock or paper, I don't win. But if you play scissors, I'm like, yeah. Okay, so right? So yeah. So why would you play this game? If you're column? Well, because I'm your boss, or I'm your advisor, or I'm the professor who grades your test. So then you play the game with me, right? So there's some outside incentive or something. So here's the equilibrium. So the row player it does want to play the last column, but if the row player just tells the other guy he's going to play the last column, what will the other guy do? Not play scissors, right? So there's no advantage in doing that. So what I'm going to do is, it's weird. So these strategies can be complicated, right? So I'm claiming, let's let that be the strategy. I'm playing this row. Doesn't play the first one at all, plays the second one this much, and the third one this much, and the last one more, because it's sort of an advantage. I don't know why. It's sort of just, that's the way the linear program solves, or the game solves. And the column player has this weird strategy. And again, what's the payoff? It's a weighted average of pure strategies. So, right? So what I'm doing now is I'm multiplying this matrix A times this column. That's all I'm going to do. So I'm just going to multiply the first vector, the first row. I'm going to take the dot product with the column vector, the column player. So that's what I'm doing here. And you see that the expected payoff for this first row is negative 1/3. So the row does not want to play this one because he loses. Right? And you can see that the row doesn't play this one because the row player has a 0 in terms of its probability of playing the first row. Okay, and you can do this again. You see a 1/6, you see a 1/6, and you see a 1/6. So now the row is sort of happy playing any of these things because all of these are good for it. Positive numbers are good for the row player. Okay? If you fix the column strategy, then the row player will just pick one of these things as its best response. But it's also, so the payoff, you can calculate the payoff. It's obviously going to be 1/6 because it's only playing a mixed strategy on these, and the distribution adds up to 1, so it's going to be 1/6. So now the column player, every column player is 1/6 if you do this other thing, if you multiply the other way. So that's why the column player may play any one of these strategies in this strategy. Okay? So both are only playing optimal strategies. Okay, so it's an equilibrium. The row player can't get any more if he switches his strategy. He's already getting the max row. Right? The column player can't get any more if he switches if she switches her strategy. Right? Because she's always playing the min column. Okay? So these are an equilibrium pair. Okay? That's slightly more interesting than rock, paper, scissors. Okay. So the point is, zero sum doesn't mean the value of the game is always 0 for 1 point. Okay, zero sum just means one person pays the other. Okay? So that's all it means. Okay, so, and this complementary slackness is they only play optimal strategies, and they, so therefore, this is, it's an equilibrium, and that's, you can also prove all this stuff, prove that just using that, the way we talked about complementary slackness. Okay, so now, okay, so is there always an equilibrium? So column goes first. We saw this in the thing. Row goes first. You remember now, in this case, in Rochambeau, what we said is if we fix the y, the best thing that the x player can do is just pick the best row. Right? You do a times y, you get a column vector, and you pick the best value for you. So you could always play a pure strategy. Okay? This max inside of the min y is hard because you have to play against any possibility of what the x does. Okay? But the max x is easy. You just pick the best row. Okay? And so on. What's the value of R in Rochambeau? What's the value of R? Rochambeau is this rock, paper, scissors. Well, what is y going to do? They're going to play 1/3, 1/3, 1/3, and my value will be 0. It doesn't matter what I do. I have an equal chance of losing or winning. Okay, so the value of R there is here. Here is the same thing. And what's the value of C? It's going to be 0 as well, right? Because the row player will play 1/3, 1/3, 1/3, and the best thing the column player can do is 0. Okay. So this is weak duality. So at equilibrium, we had this proof in the thing, in the homework. In the last lecture. I'm not going to go over it again. But this is at equilibrium. Basically, it says when you're at equilibrium, first, the weak duality just says if the role player gets to go last, yeah, this is reversed a bit. But if the role player gets to go last, its value is going to be higher than if it went first. That's all. And the column player, if it gets to go last, its value is going to be lower than if it went second. Okay? So that's all it's saying. And then you can prove that the equilibrium point, once you have no incentive to change, it is an equilibrium. Okay? That's what I argued by example last time. Okay? So it doesn't matter who plays first. That's a review of the thing. Okay, so now I'm gonna prove approximate equilibrium. Okay, so now I'm gonna take a strategy pair x, y, and an equilibrium at an equilibrium. So I'm defining this thing called C of x. Okay, it's the min y where xt of a times y. Okay, that says I'm fixing x, and then I'm finding the best response. Okay, by the column player. That's what C of y is. And R of y is you're fixing x here. You're fixing x. Now you're fixing y, and then you're finding the best x to play against it. So that's good for the row. So the R means good for the row, and the C means good for the column. Okay? Now a strategy pair is a pair where you have equality here. You say R of y is equal to C of x. So R of y is sort of this vector of a times y, and you take the min, take the max. Or in this, C times x, C of x is xt times a, and you take the min. And so if you have a strategy pair, x and y, these are going to be the same. Okay? Or, another way to say that is R of y minus C of x is equal to 0. Okay, so that's kind of not very interesting. But now an approximate equilibrium, now R of y is always greater than, R is sort of in general, there's some y where it's greater than C. Okay, so this is positive. Now, if you make them close enough, then I'm calling them an approximate equilibrium. I would like this to be 0, but, okay, say I'm a little off. Okay, so that's the approximate, what I mean by approximate equilibrium. Okay? Because R of y is greater than. Okay, so now what this says is R of y is the R's best response to y. Okay? And it's only a little better than y's best response to x. Okay? That's what it's saying. Okay. So how are we going to prove it? I already told you. Okay, so this should be fast. Using geometry, using a fixed point theorem, or using multiplicative weights. Which one are we going to do? C. But you can prove it the other two ways. The original proofs were using it. One of the original ones was using a fixed point theorem. A classical one is using geometry. It really is using the fact that if you have a convex set and a point, you can separate them with the hyperplane. So it's a very geometric proof there too. But I'm not going to do that. So it's kind of easy to do this, but it's sort of, you just have to get everything set up right? Because there's nothing fancy here. But, once you get y and x and things are going back and forth, so you got to be a little careful. Okay. So what you're doing is this. You're trying to find, this is R of y star. It says the role player gets, R of y is, the role player gets to do anything it wants against y star. Okay, that's what this is saying. And that should be good for the role player. He should be able to maximize like crazy because he already knows what the min player is doing. Okay? And this is the other way. This is the column player. She gets to minimize against x star's row player. Okay? Okay, now I'm going to say the difference of these two are small. So in some sense, you can think of those stars as a defense. Right? I'm announcing what I'm playing. I'm announcing I'm playing 1/3, 1/3, 1/3. Now, if you do you could do whatever you want. Okay? So remember experts. You have n experts, t days, and L star is the total loss of the best expert. And the multiplicative weights method yields the loss L, where L is less than or equal to 1 plus epsilon times L star plus log n over epsilon. This is what we proved last lecture. Okay? Do you get that? That's just the framework. Okay? So if we have a weather station, we get to pick, and we pick using our distribution, we do as well as the best weather station almost. We lose a little bit here, and the best weather station was wrong 10 times, or L star times. We only lose a little bit more than that here, plus a little bit plus this additive factor. Okay? Okay, so that's the theorem we're going to apply to prove, to find an approximate equilibrium pair. Okay, so for now I'm going to cheat a little bit. I'm going to assume the A only has positive entries, just for the heck of it. But it all works anyway. But it has payoffs that are only between 0 and 1. I mean, if they only has positive entries, you could just scale the matrix and it's fine, right? So that the maximum value is 1. But there's versions of multiplicative weights that deal with losses and gains, so it's fine. Okay. So for T, you have so I'm going to do this for days. Remember, in the experts framework, we had days. Each day, the expert predicts something. Each day, the adversary assigns losses to each expert. So the M pure column strategies are the experts. So each day, there's a column strategy. Okay, I could either play column 1, column 2, column 3, column 4, right? That's what the expert is. And the expert I always plays column I. But we're going to take a mixture over these, or a distribution over these. A mixture just means distribution. Okay? Using multiplicative weights and produce a column distribution. So we're going to keep doing this, and it's experts. Somehow losses are going to be assigned, and we're just going to play multiplicative weights. So then that will produce distributions over the columns. Okay? Okay, so YT is a distribution on day T. That we're just defining some notation here. So remember, what's the distribution? It's proportional to the weights, the multiplicative weights. That's the distribution. That's the probability we choose expert I is proportional to WI from last time. So each day, the adversary, it gets a distribution. It sees what's the distribution you're playing, the column player is playing. So it does the worst thing for the column. It just picks the best row for it and plays that. So it picks its purest distribution. Okay? So it chooses a row that maximizes the column's expected loss. Okay? These are just losses because they're positive and the row is maximizing. Okay? So XT is the indicator vector for this row, right? It's just all zeros except for the row that it plays. That's 1. Just to make it easy. So this is what it does. There's some column player. So the first day, maybe the column player is playing uniformly, right? And maybe the best row to play against that is the first one here, and so on. The second day, maybe the best row to play against the distribution that develops is this one, and so on. So this is what happens. Is that clear? So this is the pattern of losses that are assigned. Okay? This isn't the pattern of losses. I'm sorry. The losses are not in the table, but the X player's response is what's in the table. Okay? Okay. So every day, do you see 2 distributions here? You see a distribution for the Y player. We had one every day, right? So over time, we should just average them. That gives us another distribution over the column K players. What about, how do we get the distribution over rows? Well, we have all these plays. What if we average them? That's the distribution over the rows. Okay? So that's what we're doing. So in some sense, what I'm saying is I'm going to tell you my original distribution, like not rock, paper, scissors, but let's do rock, paper, scissors, and boss. Originally, I might play them all. The column player may play evenly, and the row player will just play the best one every time. And then what we're doing is averaging what happens over all time for both of the players. Okay, so that's what I'm doing here. Oh, no, I'm doing something different here. I'm taking the best distribution. I could have averaged as well. So I'm picking YT that had the best. Every day, I play the multiplicative weights is play in a distribution, Y sub T. Okay? And now, that day, what does X get to do? It gets to hammer it. I'm gonna mess you up. I'm gonna make you pay a lot. Okay? But what I'm gonna choose is the day the Y player did the best. It's like I got all these distributions every day, and every day the row player gets to play. So I'm going to pick clearly one thing I could do is I could have averaged them, but I could with this, I do it both ways. This time I did it this way. So what I'm doing is I'm picking the strategy on the day that I did the best as a column player. And what is the best is I held up the best against the X's response. So that's what I'm saying. The best for me is minimizing. Argmin. Okay? And the row player, to get a distribution, I just average. Okay, so now I claim that these are 2 epsilon optimal if I use this many days. Okay, 1 over t is the number of days, capital T. Okay, so the row player payoff against y star is the max x of x against a times y star. Do we see that already? We see that value already? So loss on day t, xt times a yt, is greater than yr times y star. Because we chose the best y star. So every day, the x player does a little better than he does against y star. Every other day. A little better or at least as good. Okay? Every one of the days, whatever yt was played, the x player that day did well. Right? Did at least as well as he would have done against y star, because y star is is the worst one for him. Okay? This is a triviality, right? But it's just the definition of what y star is. It says y star is the one where this is minimized. It says every other day it's bigger, this payoff for the x player. So now that tells us the algorithm has a lot of loss. Okay? The x player is hammering you, right? It's the lower bound on the loss. It says, okay, I'm getting you. And every day I get it so much loss. So the algorithm doesn't do too well. That's what it's saying. I mean, the algorithm doesn't do too well. L is big. Okay? Okay, now let's think about the best column. Okay? Now, against this distribution X. Remember, X is the average distribution. At the end of the day, the best expert is the best response against the average distribution. Right? That's what the best expert means. The best expert is the expert who has the smallest loss. So it's the column which played against this distribution, which is the average of all days, that minimizes the loss against this distribution. Okay? So the best column against the sum of xta, right? But that's not what we get there. We get a 1 over t, but it's just the scaling, right? T times x star is equal to that. So best column against t times x star times a. And so therefore you get that the loss, the best expert's loss is at most t, right? It's just scaling. The t comes from the fact that we're scaling, we're averaging. Okay? So the total loss is the sum over t of xt times a against every day. That's every day. Okay? And now, but my strategy x star is just divided by t, so I pull it out. It's linear. Okay? So what is this min y is the best column against this guy, against this average distribution. Okay? That's what we're saying. So we're saying the loss is less than t times, this is c of x star. Okay? Okay, so now multiplicative weights, we have a theorem. We say that L, we have 2 quantities here. L, which has R of y in it. And we have L star, which has C of x star in it. Right? And we were trying to find a C of x star and an R of y that are close together. Okay? And what does multiplicative weights say? It says, well, L and L star are close together. Right? Roughly. Does that make sense? Okay. So that's all it's saying. And now I plug in. I plug in for L, which is that it's T times R y star. And I plug in for L star into this formula here. And I get T times C of x star. And then I do a little algebra, and I see that the row player doesn't do too much better, it doesn't get too much more than the row player against y star can't do too much better than the column player against x star. Okay? So now you can subtract. I'm just subtracting the 1, and now I get this nasty expression here. And now what I did is I said every loss is at most 1, and t is log n over epsilon squared. And if you put a 1 here, you get an epsilon. If you put log n over epsilon squared here, you get an epsilon. So you get 2 epsilon. Okay? So, yeah.
Another question. So we're talking about like the program and the best expert health are putting upper bound on it.
Uh-huh.
I'm kind of curious, how come it's not like health is equal to that? Why is there an upper bound? Is that the distribution that they ended up putting?
It's equal.
It is equal?
Yeah.
Oh, okay.
The other one is not an inequality. You're right. He just said, my argument here is that he's saying this argument really was saying these are equal. So that's correct. Okay. So for any epsilon, so now this is an approximate equilibrium. Now for this proof works for any epsilon. So what should I do to get an exact equilibrium? I want this to be 0. So I just take it to 0. Okay? So, yeah, something about math. You have to say something about math here, right? Because you have to take an epsilon to 0, right? What does that even mean? I don't know. But we can do it, right? We've done it before. So let's just... Like mathematicians, they make you take, what is it called? Analysis? Yeah. You're talking about the unit interval for the whole semester, but they never tell you you're talking about the unit interval. It's really annoying. Okay, so, but they talk about Borel sets and finite subcovers of blah, 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 and blah, blah, blah. It's not good. So, but it's good, but I guess it's good for somebody. So other proofs, we can use geometry and linear programming. So the complexity, this is cute because it actually gives you an algorithm to produce the equilibrium. A very simple algorithm. You can produce the equilibrium. You're solving the zero-sum game to some approximation. Okay? And this is basically linear because n times m is the number of entries in the table. Linear programs take longer per step, right? I mean, that's sort of roughly they do. Okay? There are faster linear programs, but it's still much slower and complicated. So if you just want to get something that's quick and fast, and gives you a pretty good approximation, this method actually works. Okay. Okay. So now, also works with both using multiplicative weights. You can set this up a number of ways. I could have set it up where I outputted the average and then made an argument too. The average response also works. Okay. So if the rest is not, it's just for fun. It's not testable. Let me just, and I don't have much time, so it's probably not even going to be understandable. So whatever. But it's pretty cool. Okay, so it's really cool. So let me tell you about it. Okay, so here's an idea for learning. You have a labeled data set, and you learn a model, and it works kind of well. It works okay, but not so good. So what should you do? You take the points that it didn't learn well, and you try to learn them with a different model. Okay? This seems like a very natural thing, right? If you didn't do well on some of the points, you look at them, you say, what was hard about those examples? Right? Even we do that. Like, what questions did I get wrong? Let me think a little more about them. Right? Does that make sense? Okay. So this is sort of and now after you get a bunch of models and you put them together, can you get a better predictor? Okay, so that's the idea. So it's a very natural process, again. Just like multiplicative weights, the natural process is don't trust that guy when they sucked, right? So that was a natural process there. This is a natural process, too. If you tried an algorithm, it doesn't work on some part of your input, let's try again on that part of an input with another learning algorithm. Okay? And then once you get a bunch of models, what are you going to do at the end? I don't know what to do. If I have a bunch of people and they're voting, we're in America, we vote, right? Does that make sense? Okay. How do you analyze? Okay, so here's the thing. How do you find a hyperplane that separates all these points, right? It's sort of a problem. What about half of them? That's a triviality, right? You can just scan, it doesn't matter, right? You can just, half of them you can, you want to find a hyperplane where on one side, half and half are, more than, half are pluses and half are minuses. And that's ridiculous. All of them are, half of them are pluses and minuses in the beginning, so it's a triviality. But an arbitrary line works, right? It's already split half and half, right? Now you can scan, but it's useless. It's kind of a useless algorithm. But what if you have an algorithm that just gets a little bit more than half the points correct? Like on one side, it's 49% pluses and 51% minuses. The other side, it's the other way. Okay, that's what we say. What if we have an algorithm? That would be good. So that's called a weak learner. That's the person who's getting 51% on the exam. That's weak learner. Okay, so, okay? Yeah, well, that's a weak learner. Okay, so it produces a hypothesis correctly for 1/2 plus epsilon of your input points. Okay, a strong learner produces a hypothesis correctly on almost all the points. Right? We're thinking, obviously, for certain epsilons and mu's, you can mean anything, but I'm thinking of mu as very small. Can one use the weak learner to produce the strong learner? And exactly like I just said, well, you just do it, and then you work on the points you haven't done well on, and then you try again, and maybe the points but then you have to apply that point to all the points, and maybe now, on average, some of the points you did well on the second time, and some on the first time, some on both times, and then you try to work on the ones you got wrong both times a little harder, right? This is what you do. Okay? So boosting is the idea of using a weak learner to produce a strong learner. Okay? Can we do this? If yes, how do we do it? Multiplicative weights, because I told you that. Okay, the endpoint. Okay, so they did this whole weak learning is strong. There were all kinds of blah, blah, blah papers and blah, blah, but then in the solution was multiplicative weights. And there's prizes, and this is in all this skit-learn. So here, the weird thing is the experts are the points. And here the experts, the adversary is the weak learner. So you have an expert for each point, and when do they lose? When does an expert lose? Yeah, these points are bad. They don't want to be classified correctly. Okay, for an expert to lose, it means the adversary classified them correctly. Okay? They want to be misclassified. So they lose when they're classified correctly. Okay? Okay, learner wants to maximize the probability of classifying a random point correctly. That's what it's doing. So the strong learner will come from the adversary. So this is what you do. You do this using multiplicative weights. The role player, you just do multiplicative weights on the points, and the column runs a weak learner on the row distributions. Okay, so every day now you have a distribution over points. Now instead of a subset of points, I changed what the weak learner does. It's working on a distribution of points, but on that distribution, it should be right a little bit more than half the time. Okay, that's 1/2 plus epsilon. And it outputs a hypothesis that day. And then in the end, after you do this for a while, you output the majority. Whenever you want your final hypothesis, is you think about your hypothesis on day 1, hypothesis on day 2. And these hypotheses, where do they come from? The learner. Right? The learner learned some hypothesis. That hypothesis, for every point, predicts a value, a label. Okay? And it's right 51% of the time here, maybe 51% of the time here. So if you take the majority of a bunch of times when it was right about 51% of the time, you would expect with good probability that the majority will be right. Right? Yeah. It's set in a binary setting right now, yes. I mean, maybe it doesn't have to be, but I don't know. Okay. So the intuition here is that on average, all the hypotheses are right 51% of the time. And so now it says, over time, every point gets that property, that it's going to be classified correctly on 51% of the hypothesis. So it's converting this column statement into a row statement. Okay? That's what it's saying. Okay, so this should be surprising and amazing, and I should dance around, except it's not pretty when I do that. So, okay, so at least, I mean, yeah, okay. So, okay, so in the end, you're thinking of a bad set. Which points are classified incorrectly? Okay? At the end of the day, you want to say which ones are classified incorrectly. Okay? So what does that mean? The majority of these hypotheses are wrong for any point in the bad set. Okay? The majority of the hypotheses are wrong. If the majority of the hypotheses are correct, it's going to be classified correctly by this algorithm. So the bad points, the ones that remain bad, are all the ones where the majority of the hypotheses on different days are wrong. Okay, so now let's do an analysis. We're going to do an analysis. Remember multiplicative weights. Every day we have a weight for each expert, and here the experts are points, so each point has a weight on time day t. The potential function we're going to talk about is the sum of the weights again, exactly like we did before. Now, if x is in S bad, is a good expert, so it loses less than half the time. Okay? So what it says is for anybody in the bad set, its weight is pretty large. Okay? Remember when we looked at this potential function on weights, we produced a lower bound, which was our best expert. It has a lot of weight, and an upper bound somehow. But right now we're producing a lower bound on this potential function. And what we're saying is for anybody who's a good expert, he loses, right? They lose when they're classified correctly. Okay, when they're classified correctly, you multiply them by 1 minus epsilon. And since they lose less than half the time, it means that they only got multiplied by 1 minus epsilon t over 2 times. So the total weight is at least the number of bad elements times the weight of a bad element. And the weight of the bad element is pretty large because they didn't lose very often. Okay? That's what this, and very often is t over 2. Okay? Now, on the other hand, the adversary is doing good, right? It's hammering the distribution with loss. It's giving it a lot of loss on average. More than half the distribution gets lost every day. That's what it's saying. So this says the loss at time t on expectation is bigger than 1/2 plus epsilon, plus gamma. Okay? So now, what's the weight on time t plus 1? Now I'm going to prove an upper bound on the potential. Okay, so I proved a lower bound on the potential in terms of the quantity I want. The quantity I want is the size of the bad set. Right? I want to say there's not very many points in the bad set. So I'm saying that this weight function gives you some sort of upper bound on the size of the bad set, right? This weight is greater than something times this bad set. Now I'm going to prove an upper bound on the potential function here, right? So it says that what you do here, it says you lose on at least half the distribution. So that tells you for half the distribution, or a half plus a little bit, you multiply half the distribution by 1 minus epsilon. So all these people, these losers, lose weight. I mean, I guess in this society it's good to lose weight, but here it's not, right? Okay? There's times when it wasn't, okay? You could die if you lose too much weight. So now you add this up, you do some work. This is just this 1 plus epsilon times this thing. This is E comes up a lot. So, you think of the E function, and this is a line. This line is below the E function, and that's why you get this. Okay? Okay, so that's there. Now we have an upper bound and a lower bound. And what we want to upper bound is the size of this bad set. We want it to be small. Okay? So we put them next to each other, right? The weight at the initial weight for these things was 1. You had a uniform distribution over everything. Okay, so now you have this inequality. You say the size of the bad set is less than some garbage here. Okay? Let's see what the garbage is. Okay? Let's try to isolate it all. So there's that. You start taking some logs, and you do this stuff, and then you do some more stuff. Right? We're just replacing stuff. How are we doing? Oh, yeah. Okay, so then finally we have this ln. We just sort of move things around. We get ln of S bad is less than mu. this t, this log here was less, it says this log is less than this gamma squared t over 2. And what I did is I picked t to be right? If I put in this value here, right? If I put in this value. I mean, this is weird because the thing that's non-intuitive here is gamma squared is smaller than 1. It's a small number, right? Okay, so the gamma squared is small, and I plug that in. I get ln of mu. So it says that the fraction, this log of this is less than the log of this. So you get rid of the logs. And it says the fraction of bad points, the total size of the bad set, divided by the number of bad points, is less than mu. So therefore, the rest of them are good. So you get 1 minus mu of them that are correctly classified. And that's it. Okay? And so that's it. So there's some caveats. I said the weak learner works over points. It actually works over distributions of points. You can fix that by making copies of points to simulate distributions or whatever, right? There's some way to sample. Okay? Again, it's coded in. It's called CART. There's many versions of this algorithm that are coded into learning packages